I will post again. You saw I already start posting video lectures, and I will post this as well. So please let me share my screen with you. And now you may see my screen and you may see my slides. And hopefully. And now we will be talking about turbulent combustion. So this is really important lecture and we spent time on it. Please take it seriously. Please make your notes, you have slides, and please see this video a couple of times as needed, because realize turbulent combustion is something really critical, really very important. And why people face difficulties with combustion? Because most of the time combustion flame is turbulent, and turbulence itself is a really difficult topic of study, of investigation. And that's why actually, since combustion is difficult to investigate, that's why, because turbulence is difficult to investigate, people are facing problem with turbulence. So and at this point, I want you to recall the story that maybe I talked at first lecture. So, you know, when I finished my PhD, second PhD, when I came as a postdoc to Stanford, I was selfish and proud of me because I thought that I'm expert in turbulent combustion. I thought my dissertation was about turbulent combustion. And imagine that when I came to Stanford, I realized that combustion is actually chemistry. Chemical reactions, chemistry plays a role there. And I knew very little about chemistry at that time. And also, I realized that turbulence is something statistical tool. Most likely people use correlation function. People use some kind of statistics when they talk about turbulence. So, and I didn't know, I used deterministic description of turbulence. So I realized that I knew neither turbulent nor combustion, I knew nothing. Well, now I know a little bit more, and that's what I'm going to teach you now. But please realize that there are really different approach to turbulence and how we do it. Many of you are taking my fundamentals of turbulent flow class. And again, I tell you that what we are dealing here is fundamentals of combustion. Fundamentals means that we will talk about only very basics. I'm not expecting you to be expert in turbulent combustion because there are very few experts worldwide. But I want you to understand the approaches people have, what are easy point, what are key point, and that you should be able to learn. So please remember, so you already know zero-dimensional combustion, that's what you have dealt in previous sessions, and you also know one-dimensional combustion. I don't need to repeat this, you know planar flame front, how it propagates, right? You know it. That was chapter 6. And then I told you that why we talk about multi-dimensional combustion, because this planar flame happens very seldom in reality, almost never. So there is, it's what we see here, planar flame speed, flame thickness, it's some kind of, also adiabatic flame temperature, it's some kind of etalon to which you compare your practical reality. Planar flames are not like this. Planar flames propagate faster. Why? Because planar flames are usually corrugated, they're curved, right? So as soon as your flame has larger surface area, it consumes more fuel per unit time and it propagates faster. With some velocity SW, or sometimes we call it UW, which is larger than SL. Why? Just because of geometry. If you consider smooth surface and corrugated surface, definitely corrugated surface has larger surface area. So corrugated premix flame should propagate fast. And basically, that is the scenario we deal with, that real flames are curved. So the flame gets corrugated and accelerates. They push compression and shock waves. They heat fuel, and eventually you may have explosion somewhere ahead of the flame, secondary explosion, which lead to detonation. This, what you see here, it's worst scenario. Typically, we don't have it, but we do have this stage, flame acceleration and corrugation. And here, when we investigate it, I would already ask you, why does a flame accelerate? And the answer is, you already know that it depends on many reasons. Remember, we consider several configurations how it may happen. And one of the reasons that flame accelerates are combustion instabilities. Remember, we consider combustion instabilities. You remember chapter 7, chapter 8, when we combine combustion instability with acoustics, that's what you know. That is a topic of your homework number 4 that you are doing. But, and that's, remember, we arrived to the point how flame gets corrugated. And here you should realize two things. That for decades, for most of the time, people assume that that flames are usually turbulent. And people say that flame is corrugated due to turbulence. And that was a very difficult point because people say, okay, so flame is corrugated because of turbulence. Okay. Then I can say, okay, so to know how flame corrugates, to know how flame propagates, I should know turbulence, right? If mouse is scared of cat, he or she should investigate what cat is, right? Otherwise, no way to survive. So we should investigate turbulence. And since we did not know what turbulence is, we did not know how flame propagates. But here, luckily, situation is not so difficult. There are many situations, and we will consider many of these situations, several of these situations in our class in April, in the lecture that left. Very often it happens that turbulence is not so crucially important. It can be weak, it can be supplementary. And then we are lucky. Then we are able to solve the problem. Remember, in fact, even laminar flames are corrugated, and they can be corrugated due to their combustion instability. So remember this picture, and I show you also a picture of a flame front in previous lecture, which is non-corrugated but laminar. So even laminar flame may be corrugated. Here there is no turbulence, that's vorticity. But in reality, even here, when I have laminar flame, I provide vorticity. So turbulence may exist. And so let's discuss what turbulence is and what we can deal with turbulence. So to answer this question, I should say that there are several approaches how you can consider turbulence and what you can investigate. So let me start with this. I make a pause for a minute so everyone like wakes up and is ready to listen. Okay, so in fact, I will tell you something. Remember, I tell you that what is our key parameter for flame propagation? It's thermal expansion, theta, right? It's density drop at the front. Here it is. And typically it's quite large. But if you take my turbulence class, you may remember that basic turbulence theory says that density is constant. So basic turbulence theory is not ready to consider reacting flows. Basic turbulence theory assumes that density of fuel and burnt matter are the same. So density is constant, you talk about incompressible substance. And I should tell you that for a long time, unless all theories of flame propagation, theories, not simulations, just not experiments, of course, but theoretical approach, were limited to the case when theta is equal to 1. That is when the fuel and burnt matter have the same density. Moreover, most of theories were employ two-dimensional geometry. You may say it's ridiculous, it's stupid. Well, people had nothing better, and they still be able to provide something to describe flame propagation. So let me follow this. So what happened? Let's say theta is equal to 1. So what does it mean? It means the density of the fuel and density of the burnt matter are the same. Everybody understand it? So what does it mean? Remember, I tell you, fluid mechanics does not see temperature or chemistry. Fluid mechanics sees velocities and densities. So if my burnt matter and fuel mixture have the same density or close density when theta is about to be 1, it will mean that my flame, which you see here on the screen, is nothing but discontinuity surface. It's an imaginary line. And it means that flame cannot influence the flow because the flow does not see it. I see it, you see it because we colored it, right? But flow would not see a flame unless there is the difference in density. Flow understands only density. So in this configuration, what is turbulence? How it looks like? Well, we talk about basics here, but if you take my turbulence class, some of you took it in the past, you may remember that there are like 11 or more shades of turbulence. So there are many vortices, it's essentially 3D and so. But key points that you can consider spectrum or vortex. So if I have vortex, how flame interacts with the vortex? So look here. So I have a flame initially planar or not, and I have a vortex. This is a vortex. Vortex axis is perpendicular to my plane of my screen, okay? And then this vortex takes a flame, elongates it, and that's what I see. Do you understand? So this is flame vortex interaction. Flame interaction is a single vortex. And that's what what we call kinematical drift. Why we call it kinematical drift? Because it's poor effect when I took vortex and elongated the flame. Okay? Here, there is nothing else. And that's how people investigate flame turbulent interaction. Is it realistic? It's not realistic. Why? First of all, because what do we know about turbulence? Turbulence is essentially three-dimensional effect, right? Three-dimensional feature. Remember we talked that if you have, why? Because turbulence is rotor of vorticity. Turbulence is a rotor of vorticity. And then when you take rotor, you take curl, it should be intrinsically three-dimensional. That's why when we talk about ocean, when we talk about something happening in space, it's not real turbulence. Turbulence should be essentially 3D. So if turbulence is 3D, then I have three vortex in all directions, in all planes. Here I may see plane X, Y, Z, right? It will be planes in X direction, Y direction, Z direction. So when I consider compare picture on the right to picture on the left, what can I say? On the left, my flame propagates perpendicular to the vortex, correct? But in reality, I have vortex which are perpendicular to the flame. Vortex axis are perpendicular to the flame. And vortex axis which are parallel to the flame. Agree? All combinations. So in reality, I have flame propagation perpendicular to the vortex axis and parallel to the vortex axis. Do you understand this? You may say, and what? The following. If I am here, if my thermal expansion is 1, then what? Then flame does not see propagation, its propagation along the vortex axis, because there will be this vortex does not feel flame. But in reality, I do have density drop at the front, right? What does it mean? It will mean the following. It means that in reality, I have such a centrifugal force. To explain it like this. Let's see something. I wanted to, okay, I stop sharing. Okay. Yeah. Now I should want to share my screen to explain it. So let's see here. What is it? Assume I have a flow and I have vortex which rotated. What does it mean? If I'm here, it will mean that if I rotate it, assume I have rotation like this, like on the next screen. What rotation means? Rotation provides you centrifugal acceleration. Do you remember centrifugal force, centrifugal acceleration? Imagine you have like a circus and there is like biker which drives very fast. You know, this biker can go along the wall. Why? Because there is a centrifugal force which protects him or her to fall down. The same story here. Instead of a biker now, I have a flow. Imagine I rotate it. I have flame propagation along the vortex axis. So what my vortex does? My vortex push heavy fuel outward and light bird matter downward. So it will extra flame elongation. And this effect is very important. It's really related to thermal expansion. Okay? And since this effect is really related to thermal expansion, it's extremely, extremely important. Because what you see at the left-hand side? At the left-hand side, I tell you classical approach. Then theta is equal to 1 and in C two-dimensional picture. When people accounted for kinematic drift. Now we know two things. That in fact, kinematic drift, I will show it later, it's weaker than it was expected because of thermal expansion. And you have dynamic effect. You have burning along the vortex axis, which is dynamical drift, centrifugal force. And it may very often, it may dominate over kinematic drift. I will repeat it when it comes to formulas, but please remember this. That's conceptual. Okay. So what do we know about turbulence when we consider some kind of applications? Let's say I consider classical engine, car engine as example. There are many devices we can talk about with bottom dead center, top dead center, how it and piston motion. So what turbulence does here and what should I know? First, you should know that in combustion we deal with complicated chemical kinetics. So if I want to investigate it, I should know how turbulence interacts with chemical kinetics. Second, so what are the sources of turbulence if we talk about engine, but it is the same in turbines or whatever? First of all, it's injection, intake. So when I put fuel, I inject fuel in my burner, I generate turbulence. Second, in my engine, and in any kind of internal combustion engine, you typically have piston, right? Piston goes up and down, and when you push this piston, you rotate your wheel. So piston motion definitely generates turbulence, right? And eventually, you have flow distortion. And as I think at one of the lectures, it was lecture second, I showed you some kind of movies, but it didn't work out. Here it will work better now from my screen. Also, there is flame propagation itself. Flame propagates. And since in reality there is a big difference between burnt matter and fuel, flow is affected by flame propagation. Please realize what is a flame. Flame is also like a piston, like a semi-transparent piston. It's a wave that propagates and pushes the flow. It's important. So all these waves of turbulence should be counted. Now, in terms of geometry, so what types of turbulent flows you can consider rotations? If you talk about, for instance, engine. Here you have so-called squish, it's rotation in RZ plane, and that's what typically investigate. But also there is swirl, rotation around Z axis, ensemble, rotation in R axis. All of them participate in turbulence. Does it make sense? Ask me something. Everything is too complex or too easy? I believe too complex.
Dr. Ackerman, in the previous slide where you were showing the case for the 3D, so yeah, right there. So you're basically saying that if the thermal expansion is high, let's say 5 or 8, we also have ignition due to vortexes?
Not
or
ignition.
not?
No, we don't have ignition, but we have flame propagation.
Okay.
So what I want to say, very good point. So what I want to say, yeah, please go ahead.
Yeah, so the flame propagates due to vortexes in all directions besides stretching, right?
Yes, exactly.
So it is, okay.
Exactly, besides stretching, that's very good point. Besides kinematical drift, you call it stretching. That's very good point. Yes, but so flame propagates, besides stretching, flame propagates in all other directions. Or let's say flame propagates in one direction, but there are vortices in all directions. But if I'm on the left-hand side, I would not feel, my flame would not feel any other interaction except for stretching.
Stretching, okay.
Because there would be no difference between fuel and burnt matter. But okay, because fluid mechanics knows only density. As long as, if I'm on the left-hand side, my density of burnt matter and fuel mixture is the same. So any rotations would not provide any centrifugal force. But what we see here is that there is centrifugal force, and it may dominate. That's very good point, and we will talk about this in terms of formulas. Very good point. Now, so we will, now what we'll do next, it's really important and really nice picture. And please now pay attention to this. We'll be talking about so-called regime diagram. Sometimes people call it Barrier-Borge diagram. Sometimes people call it Peters diagram. There are different ways of how this diagram presented in the literature, but that is something really important. So you may, because what we talked so far that I told you, that there are different ways of turbulence, how it behaves, depending on geometry of source and so on. So now I would tell you that there are different regimes of flame propagation. It means that turbulence may influence flame in different manner. And here I would like you to show how it happens. I would like you to show how flame propagates and how these regimes go. What are this and how flame interacts. So please, this slide, next slide. Okay, this slide, next slide, and a little bit, and this slide, that's what we have. This is something, guys, that I want you to remember. Please pay attention. So what we are talking about? Before start talking, we should talk about characteristic scales that we have. And now let's talk about it. So if I talk, so let's say I will be talking about flame, and I will be talking about turbulence, right? So they interact. When flame interacts with turbulence, what should I talk about? Well, let's say you have like two fighters, two boxers, for instance, and they fight with each other, and you want to analyze who is stronger. So what you talk about? You say, okay, this has weight of boxer one is the following, weight of boxer two is the following, and their height is the following and the following. So you measure them, right? Somehow, and make a conclusion. So now I want to characterize somehow turbulence, and I want to characterize a flame and compare their scales to make a conclusion. So if I talk about flame, what is the characteristic length scale of flame? Please tell me. How to measure flame? What is size of the flame? If I say it, so what is a characteristic measure of a flame? If I talk that flame is thick, or I can talk that flame is thin, or I can say that flame has zero thickness, what does it mean?
The laminar flame thickness.
Exactly. Yes, this is a basic measure that you have. Classical measure is laminar flame thickness. And remember what is this? Is thermal diffusion over flame speed. Laminar flame thickness, it will be characteristic size of a flame. Yes, there are other units like active reaction zone thickness or the Rayleigh cutoff, but they all related to it, right? Exactly, very well. Okay, and let's call it L0 here because very way how you can explain it. Now, and what about turbulence? What are characteristic scales of turbulence?
The Reynolds number.
Yes, exactly. But Reynolds number, exactly, very good. But Reynolds number is what? It's basically, you define it somehow, right? So you define it by characteristic scale, by characteristic velocity and viscosity, right? Like we wrote here. So basically, Reynolds number depends on the characteristic scale, right? So what is the characteristic length in turbulence? It's what we call integral length scale, correct?
Okay, yeah.
So that's true. So do you agree that my parameter, my dimensionless parameters that I will deal with should be my integral length scale divided by flame thickness? Why I put index 0 here, I will explain a little later. But do you agree that if my integral scale is very large as compared to flame, then flame it's like a blanket of zero thickness and it interacts with turbulent in some kind of one manner, right? And if, for instance, my flame is very thick like a pillow and integral scale is small, it will be different way of interaction. Do you agree? I believe so. So this L0 over LL will be a characteristic measure of a characteristic measure that we deal with. Now, velocities. We also have characteristic measure of velocity. So what is characteristic flame velocity? What can I use as a measure of velocity for a flame?
The laminar flame speed.
Exactly, of course. And what will be characteristic measure of velocity for turbulence? It will be turbulent root mean square velocity, or what we call U prime, right? Because that's how turbulence is defined. Sometimes we call it turbulent intensity. Everybody knows what is root mean square?
Yeah.
Root mean square velocity. So root mean square velocity. And that is, so the ratio between root mean square velocity and planar flame speed, it will be another measure how to see flame flow interaction. Because you may realize that if U prime is very small, what does it mean? That you have very fast flame and turbulence does not have time to interact with it, right? But if you have U prime is very big as compared to a cell, if this value is quite big, it will mean that flame will be corrugated and the turbulence is very strong. Do you understand this? Now, please realize we talk about ratio, so it's not absolute values. For instance, I may say that my U prime is 1 meter per second. Is it big value? Well, it's big value. But big is compared to what? If I have hydrogen-oxygen combustion when a cell is 20 meters per second, then it's very weak turbulence as compared to flame propagation, correct? But if instead I have very lean methane air combustion with a cell of 10 centimeters per second, or even less, like in your homework number 3, then it's very, very strong turbulence. Do you understand? So these are characteristic, we compare characteristic turbulent velocity with characteristic planar flame speed, with characteristic flame velocity. And we compare characteristic turbulence scale with characteristic flame scale. That's what we are doing. Now, you may say, why I put the subscript 0 here? Answer is the following, because it's not only turbulence which interacts with the flame, but flame impacts turbulence. So here I talk about initial parameter of the turbulent flow, because when this flow starts dealing with the flame, this flow will be modified. And it's intriguing how it will be modified. So we talk about external turbulence, which is imposed to deal with the flame, like external source, external agent. Does it make sense? Okay, but what I show it now. So please look at the formula here. I don't use screen now because I don't want to waste time, but let's see. If you talk about Reynolds number related to turbulence, so what is turbulent Reynolds number? It will be by length scales. It will be U prime multiplied by integral lengths and divided by viscosity. Remember?
Yeah, and Dr. Gemma, in that case, is that viscosity or is that thermal diffusion?
Okay, very good point. Really very good point. Excellent question. Answer is the following. Excellent point. Answer is the following. At the left point so far, it's viscosity because it's definition of turbulent Reynolds number. Please remember, this is turbulent Reynolds number. This is not Reynolds number of the flow. It's turbulent. It depends on turbulent velocity. Now, if I go like this, it really becomes thermal diffusivity. So you may say, why I talk like this? The answer is the following. What is the ratio between thermal diffusivity and viscosity? It's Prandtl number, yes?
Yeah.
How big is the Prandtl number? It's like 0.6, 0.2, so very seldom. Typically, it's about unity. But remember, if you deal with turbulence, theory, everything is by order of magnitude, by order of unity. So here, really, we can neglect Prandtl number and consider nu to be equal to thermal diffusivity because we talk of order of magnitude. And if you look at this picture, yeah, I should say it in advance. If you look at this picture, it's logarithmic diagram. In logarithmic diagram, we deal with orders of magnitude, right? So when I say that U prime divided by a cell, it's my characteristic value, you may realize that I talk about, I'm not interested, is U prime is 2 a cell or 2.1 a cell. I'm interested U prime is like 0.1, 1, 10, or 100. Okay? That's why units of the order of magnitude of 1 can be neglected here. And what will happen here? You can do your own calculations very simply. So here I use Reynolds number is U prime L0 divided by nu. But what is flame thickness? What is LL? Remember, it's nu divided by SL, nu divided by SL, and divided by, that's all. So if I substitute it here, this will be my expression for Reynolds number. So my Reynolds number is actually nothing but what? But the product of my scaled intensity, U prime over SL, divided by scaled value here. Of course, these are not all parameters you should know. We also have other things like Karlovic's number, which shows characteristic reaction and turbulent time. And you also should remember about Kolmogorov scale. So if you may remember about turbulence, so what is key point about turbulence? That there are a set of vortices. Let's say you sit in your room. Of course, if I was in your class, it will be easy to show, but anyway. So you sit in the room, in some kind of room you sit. So imagine you have turbulent flow. What does it mean that you have turbulent flow? It actually means that you have many, many vortices, okay? Of different scale. You cannot have one coherent vortex. You have many, many vortices. What is the largest vortex you may have? Largest vortex you may have is given by the size of your room, right? That's what we call integral scale. It's characteristic size of turbulence. Typically, it corresponds to the size of your chamber. Well, not all the case, because typically it depends on dimension, and also if I have some propellers, fans, perforation plates to create turbulence, then it will be different, then there will be characteristic scale. But actually integral and scale, it's your largest vortex, okay? What is useful, and what happens in turbulence? You know there is energy cascades, turbulence go from big scales to small scales, and the smaller the scales, the stronger viscosity is. And on small scales, there is a concept of Kolmogorov scale. What is a Kolmogorov scale? It's the smallest size at which turbulence still exists, vortices still exist. If you go to smaller scales, these vortices die very fast because of viscous dissipation. That's how actually happens energy transfer in turbulence. Energy goes from big cascades to small scales, right? To big cascades to small scales. And eventually turbulent kinetic energy is generated. It goes from big scales to small scales. And when you go to small scales, it dies. It dies, it dissipates because it goes to what? To thermal energy of the flow. And you may remember thermodynamics classes when we say that really it's easy to convert mechanical work into heat, but it's not easy to do vice versa. Like I said, let's do now. Due to this friction, I convert kinetic energy of my hands into preheating of my hands, but it's not easy to get it back. The same story here. Turbulent kinetic energy goes from big scales to small scales, and it dives at Kolmogorov scales, but it does not go back. So now you may realize that it's really important where is your flame size here. Is your flame smaller than the integral scale or larger? Now, is your flame thinner than the Kolmogorov scale or not? At the same velocity. So that's how we arrived in this diagram. And here will be different regime diagrams. So based on the ratio between U prime and SL and these values, we will talk about it, how it goes. Here's the same diagram, and here what I want you to explain something. Here's this picture, and here how it looks like. And you may realize if your integral scale is less than the flame scale, and if your U prime root mean square velocity is less than flame velocity, then we may say that flame is laminar. There will be no turbulence here. Your turbulent Reynolds number is less than 1. You know that Reynolds number is characteristic of turbulence, right? It should be really big to have turbulence. So there is no turbulence here. But turbulence there is otherwise. And please look at these diagrams, and here we will try to understand together what's going on here, where we are, and how things goes. Please try to understand it. So what happens here? So here is this axis is L0 over LL. So this is ratio of the integral scale and flame. So if I'm here, if I proceed in this direction, it means that my vortices gets larger and larger and larger as compared to flame front, is compared to flame thickness. If I proceed here, my turbulence becomes more and more intense as compared to flame propagation. And let's see what happens. So what we have here, let's do, if you see my mouse, my pointer here, you may see here is a ringed flame regime. So yeah, again, all these lines are by order of magnitude. So it does not mean that here something happens, but if I increase velocity 10%, something else. It's characteristic difference between the regimes. So now I'm here, sometimes call it Ringfield flamelets, or even laminar flamelets. So what does it mean, laminar flamelets? It means, what is it? It means here that, well, there is integral scale here, but it means that turbulence practically does not influence flame here. Why? Why turbulence does not influence flame here? Answer is very simple. It's because here root mean square velocity is less than planar flame speed, so it cannot change flame much. So flame is slightly corrugated here. It's not planar, but it's laminar. Remember, it can be laminar, but not planar, and it's not turbulent. Turbulent does not penetrate a flame front. And where is this picture here? It's what I'm here. It's picture A on the left. So you may see this is your characteristic vortex, right? So your characteristic vortex is larger than flame thickness. Why it's larger? Because it is at least 10 times wider, right? You're here. But turbulence is weak, so flame is not affected by the flow. Flame is just unstable because of instability, but it's not affected much of the flow. Do you understand this? Now, let me go in the screen counterclockwise. So I will go like this. And then I arrive to the regimes what we call corrugated flamelets. Here it is. So horizontal line shows when U prime is equal to SL, and this line shows when Karlovitz number is 1, which means that we say here that your Kolmogorov scale, smallest turbulence scale, is equal to flame thickness. So I'm here. So corrugated flamelets. So what is it? And please pay attention to what I'm talking. Again, please pay attention to what I'm talking now. Because corrugated flamelet regime is nice for two reasons. First, it's really a popular regime that we see in practical reality. In your engines and sometimes in turbines, that's how burning typically happens. And also this regime is nice to describe. So what happens here? Here, turbulence is already quite intense. And this regime can be described on picture B downstairs. Do you see picture B?
Yeah.
So what is this? So here, flame is corrugated by turbulence. And you may see if you compare picture A and picture B, you will see that in picture A, your flame was just playing like soccer with this ball. It does not influence, right? It is not influenced by it. But in picture B, the ball corrugates the flame. You may see the effect. Flame is corrugated by turbulence. Okay? It's corrugated and there is effect. But on the other hand, your vortex is really big here as compared to flame thickness. Do you agree? It means that here turbulence does not penetrate the burning zone. So flame is corrugated, but internal flame structure remains the same. Like imagine you sit in a train or you sit in your office and it's very huge storm outside. Imagine you're in a train, it's big storm, it's raining, it's windy, it's snowing. You're scared of it. But if you have a good roof and if you have a good enclosure, you are not affected by this rain. Yes? You are traveling yourself. Okay? It will mean that your internal structure, here internal flame structure, is not affected by turbulence. Why? Because here your Kolmogorov scale is larger than flame thickness. It means that all your vortices you have are larger than flame thickness. So your vortices cannot penetrate inside the flame. Does it make sense for you?
Okay.
That it is. So it means, and it's very nice because it means that your laminar flame structure remains the same. So your transport coefficients don't change. Your diffusion, viscosity, everything else remains the same. They are not affected by the flame. And that is corrugated flame. So flame is corrugated it's by turbulence, but on large scales. Burning zone remains the same. And why we are lucky? Because that is the best regime you may use to develop theories. Because you don't need to care about chemistry here. You don't need to care about flame turbulent interaction. Because really, laminar structure does not change. Your SL value is the same. Your flame thickness is the same. It's very nice. And in fact, if I ask you how to calculate corrugated flame speed here, most likely you will say it will be proportional to surface area of the flame, right? Because internal structure did not change, SL did not change. That is corrugated flame. Does it make sense for you? Please ask me something. Okay, but what happened if I keep proceeding counterclockwise? So I go counterclockwise and my turbulence becomes stronger here. What does it mean that turbulence becomes stronger? It will mean that I have smaller and smaller vortices which may survive. And this will actually mean that my Kolmogorov scale, smallest vortex size, becomes less than flame thickness. Okay? Sometimes, and we come to the regime that people call reaction sheet, or sometimes people call it second flame. And I will explain both things like this. So what happens here? Here is what you see at picture C. You see at picture C two vortices, one big and one is small, right?
Yes.
What does it mean? It means now that I have broad spectrum of vortices, and big vortexes are still larger than flame, so they corrugate the flame as a whole. They don't change internal flame structure. You are still in rain, and this is still rain, right? That doesn't affect you. But now you have small vortices, which smaller than a flame, and they penetrate the burning zone. They come inside, they change internal flame structure. Like I say in my storm, you have your roof in your train is broken and now you get wet by rain. Now you are affected, right? You are still traveling, but you are affected by this rain. So like here. So this is still flame, what I see here. This is still flame. It's still, what I mean flame? It's still reaction zone between burnt matter and fuel mixture. It's still like zone, but what I see here, my vortices already penetrate this burning zone. They're already inside. So it will mean that my transport properties will change. I have flame-induced turbulence. So now, instead of SL, I will have another value. Instead of viscosity nu, I will have another viscosity, so-called turbulence-induced viscosity. If you remember, in turbulence class, many of you took it, we talk about eddy viscosity model. Remember, when instead of laminar viscosity, you have such effective viscosity which depends on U prime on root mean square velocity. Here it's exactly the same. Now my flame, my transport properties, my diffusional thermal coefficient, my thermal diffusivity, my viscosity, my heat transfer, they will be turbulence dependent. They will depend on U prime, because my small vortex penetrated. And what will typically happen? My flame gets thicker. You have thickened flame because transport properties become different. But this is still flame. It's still not broken. Okay. So that happens in many reactors. Sometimes in like typically in the case of supercritical combustion it may happen. So so now you may say why we call it second flame. Because here vortices are less than flame, so flame thickness plays big role. But on the other hand, why we call it reaction sheet? Because remember what is active reaction zone when reaction typically goes. Remember, if we go back to here, here is active reaction zone, which is typically 10 times smaller than thermal flame thickness, which is order of magnitude smaller. So when temperature is close to final temperature, so when the reaction typically goes, here is the chemistry. So if I look at this picture now, what happens? Still, even smallest vortex here is larger than the reaction zone. So it means that turbulence does not penetrate chemistry here. Chemistry itself, turbulent itself. You don't need to know chemistry here to describe turbulence. You just describe turbulence coupling to internal flame structure. So that is what we call reaction sheet regime. It goes between two lines, two inclined lines. So one line corresponds to when Kolmogorov scale is equal to flame thickness, when vortices just start penetrating it. And second line goes to the case when Kolmogorov scale is equal to active reaction zone thickness. So it means this is a regime when vortices penetrate thermal flame thickness but don't penetrate reaction zone. And so if I want to describe this flame on picture C, what should I know? It will be more complex than corrugated flames because I have it, but still, so I have two features here. I have flame interaction with turbulence on small scale, so flame modification based on turbulence, and I have flame corrugation on large scale like it was before. Does it make sense? Now, let me go counterclockwise more. So what happens if I go more? If turbulence becomes very, very strong here. In fact, what will happen here is that at some point, my small vortices will penetrate the active reaction zone. And that's when turbulence coupling to chemistry will happen. So what will happen actually, in that case, I will not have flame itself anymore because the front will be like corrupted and destroyed. So in fact, that's what we call well-stirred reactors. So in fact, it will be like this. Imagine I have like chamber with flame propagation, and you imagine you shake it very fast, very strongly. What will happen? That you will mix everything. So what happened here? That here is burnt matter is mixed again with fuel mixture. So I will have in this situation many like spots with burnt matter, with fuel, with flame, but there is no one flame front to talk about because flame front is spoiled by turbulence. Turbulence is so strong that it destroys the flame front. That's what we call well-stirred reactors. Do you understand this? Does it make sense? I know it's difficult, but that's something that I want you to remember. Please look at this picture one more time on this big scale and consider it. So what do we have? Again, we have like 5 basic regimes. Regime on the left, it's laminar flame. Here Reynolds number is quite small, so flame is planar, there is no turbulence at all. Ringed flamelet or laminar flamelets. What do we have here? And this is picture A, picture A on the screen. So what happened here? Flame is corrugated, but laminar, because turbulence exists, but turbulence does not, in fact, influence, does not impact flame. Does it make sense? What else I see? If I go counterclockwise, corrugated flamelets, that's the regime typically people investigate, that most popular regime. Most popular analytical regime. It goes between the line when U prime is equal to SL and the line when Kolmogorov scale is equal to flame thickness. So what happens here? Here is picture B. So flame is corrugated, and I would not say enormously, but conceptually, flame is conceptually corrugated here by turbulence. But all vortices are still larger than the flame thickness. So internal flame structure remains laminar. So if I zoom this picture and try to consider my flame front, it will happen here that still my vortex size is larger, any vortex is larger than LF, than flame thickness. So internal flame structure remains laminar. If I zoom this picture, at each picture will show me planar flame structure like it should be. So here I can employ geometrical consideration and say that the flame propagation, flame dynamics, flame velocity will be proportional to the flame surface area. It's what we call stretching or kinematic drift. Flame corrugates this front. If I keep going counterclockwise, what happens here? That's what we call reaction sheet or second flame. Here, and it goes for what? It goes when flame thickness, so when Kolmogorov scale lies between thermal flame thickness and reaction zone thickness. So what does it mean here? It means that I still have, sorry, my slides go in the wrong directions, but I think you see it. So what is here? This is picture C here. It means that now I have big scale, large scale vortices and small scale vortices. My vortices now penetrate the burning zone. So they modified laminar flame structure. They modified transport properties. My flame is now influenced by turbulence. My transport properties, like eddy viscosity model works. My viscosity now is a function of turbulence. My thermal conduction is now a function of turbulence. My Prandtl number will be now not real Prandtl number, but it will be something like a function of turbulence. but still I have a flame, and I have big scale vortices that still corrugate the flame as a whole. And here still turbulence does not deal with chemistry because my vortex is still larger than active reaction zone. And if I keep going counterclockwise, what will happen? It will happen that turbulent scales will be smaller, turbulence penetrate chemistry and destroy the flame as a whole. So here I don't have entire flame as a whole. I have just mess up. Do you understand this? I know it's difficult, but that's something I want you to understand. Please ask me something. That is what we call Peters diagram, turbulent regime diagram. So, and why we put this diagram? So now you may realize the following. That do you agree that even just before start talking about any formulations, that in these regimes, flame interaction with turbulence will behave differently? Do you agree with this? And if I want to find the formula for flame propagation, if I want to describe flame shape, do you agree that formula here and formula here will be different and should be different? Because concept of interaction will be different. Do you agree with this?
Dr. Ackerman, so as the smaller eddies cross the flame front,
Yes.
this last one increases in size.
Yeah,
So
that's very, yes, that's very good point. Well, how I draw the picture here, in fact, I intentionally increase in size because I want to show how it happens. So, but in fact, yes, it will be a little bit wider in size because instead of laminar flame velocity, you may remember what is the formula for LF, for instance, for flame thickness. It will be the viscosity or thermal diffusivity divided by planar flame speed, right? But now instead of viscosity, you have turbulent viscosity, which is larger. So in fact, yes, you modified it, your flame becomes wider. Lewis number becomes modified. Because now inside flame, your transport properties becomes influenced. So yes, it can become wider. Yes, it will be. It will be. But key point still even becomes wider. It becomes proportional to what before we called LF. And that's why actually we don't use LF here, we use LL because it will be maybe influenced by turbulence here as well. Okay, more questions, please. So please, I do want you to remember this diagram. I know it's turbulence, it's not turbulence class and it's not like, but this is something that I want you to understand and remember because that's important. Now, so, and when I plot this diagram, you may say, okay, but where is chapter 7 and chapter 8 in this diagram? Where is instability in this diagram? So how to, if you talk about instability, where is it? And here I should tell you something that, remember when we talk about instability, we realize that even when we talk about instability, we realize that even laminar flame can be stable. I mean, even laminar flame can be corrugated, stable but corrugated. Now, if instability develops, what do you think? How instability interacts with turbulence? We know that turbulence promotes instability, but how interacts with turbulence instability? Will it be like a cumulative effect or can they suppress each other? What do you think? And basically here I will show you something. And this is a tricky question. And I didn't know the answer until I started cooperating with Svetoprova Chudri, who is now faculty in Toronto. We interacted with him many years ago, and that's was his idea, how to interpret turbulence with instability. I didn't know, but then I provided him with some insight and we developed something. And I will show like this. So let's forget about everything I talked here. And let's say I have a flame. And if you see my screen here, yeah, I think I can extend my screen. Yeah. So if you see my face here, so assume this is a piece of paper. This is a piece of paper. Assume this is a flame front, okay? And assume it's propagated like a planar front, okay? Now, Assume you have a laminar environment, but you have intrinsic flame instability like the real and Dow instability. So how instability will develop? So, well, at some point corrugation will start, so your flame start getting corrugated, and propagate corrugated, right? True? What does it mean? That instability needs some time to develop, right? Instability doesn't develop in a second. It needs some evolution time to develop. It needs steady or self-sustained flame propagation to get developed. What happens if I have some kind of turbulent flow, very weak turbulent? If I have very weak turbulent flow, what does it mean? That instability, well, it will be some kind of shaking, but instability still is developing, correct? It is. And you remember, the larger the size of the flame, the better it will develop, because it depends on the real and Dow cutoff. If my flame is less than the real and Dow cutoff wavelengths, it will be planned. If I go beyond this limit, if I have many real and Dow cutoff scales, then instability will develop, and the larger the flame, the better it develops. Now, assume I have vortices, I have turbulent flow, and what will happen here? And I want flame to corrugate, but I have very strong turbulent flow. I don't know what you see at your screen. Imagine I have like a very shaken flow. Can you travel in storm? It's a question. That's the point. Assume you are traveling. You take something like yacht or some kind of boat, and you want to travel. If you have some kind of wind, this wind will help you to go, right? But when you have storm, it will crash your vehicle, your ship, and you will not travel anymore. So that's the point. If I have strong turbulence, this turbulence will not let your instability to develop, correct? It will shake you out. It will shake out. That's the point. So that we should account. And based on this, we arrive to a concept of turbulence-induced regime diagram. So what you see on the next slide, I'm sorry, this we want to incorporate the real and Tau instability in this diagram. And what we have here? Here, based on this, what we have a concept like this. So it's exactly the same diagram like it was before, right? But now, well, now instead of U prime, I write URMS here, and it's the same diagram, and here I have wrinkles length. So what do we know about instability? And here again, I have classical line like I had before. So I know that, what does it mean that I'm at the axis here? What does it mean that I'm here? It means that there is no turbulence, so it's laminar regime. And for what do we know about laminar regime? For laminar regime, you know that at some point you will have the real and Dow instability cut off, which is about 100 times, by order of magnitude again, let's say 20 times, from 20 to 100, larger than the flame thickness. So do you agree that if I look at this axis, you see my screen. So what happened at point A? Do you agree that point A is a point at which instability will start develop? So if I'm here left to the point A, my flame is planar. It cannot be corrugated because the real and Dow instability is killed by thermal conduction. Remember chapter 7? But what if I go here beyond this point A? Here, instability should develop, correct? Do you understand? I know it's difficult. Forget about turbulence. You are along this line, along this axis. As long as your flame, as long as your scale is less than the real and Dow cutoff wavelengths, you have a planar flame. As long as you exceed the real and Dow cutoff wavelengths here, you will have flame corrugation. Here it is. So instability develops. Remember? Now, that's poor chapter 7, forget about turbulence. Now let's recall turbulence. What happens if I go vertically, if I increase turbulence? Here, when I increase turbulence, I will see that my turbulence will somehow influence my instability, right? Like I show you right now with this shaking, right? So if turbulence is strong, it will not allow flame to develop. So otherwise, what does it mean? How to describe it? And here I introduce a very nice concept. I'm proud of it. So-called turbulence-induced real and down cutoff. And this is showed by the solid line. So what happens if I'm here? If I'm here, or I'm here, or I'm here, you see my pointer. Here, turbulence is very, very weak. So it almost does not influence flame propagation. Flame is almost laminar. And of course, instability will be influenced by it. But if I increase turbulence, eventually I come to the point when instability cannot develop because of turbulence. And here we shift the so-called real and down cutoff. And you may see that if I'm here, what does it mean? I introduced the real and turbulence-induced lambda. Turbulence-induced the real and down cutoff. What does it mean? It means that now I need to have corrugation on larger scales to make flame stable. Otherwise, to make it unstable. Otherwise, flame will propagate. And in fact, if my turbulence is very, very strong, what does it mean? It will mean that instability will never develop. It will be just turbulent flow. So what does it mean that instability will never develop? It will mean that my Darriel and Dow cutoff scale tends to infinity. So like I say, my turbulence here will penetrate the burning zone, and my transport coefficients will change, and my Darriel and Dow cutoff will change. So if I say about turbulence-induced internal flame structure, here I say about turbulence-induced Darriel and Dow cutoff scale. That's how it goes. It's a nice concept. So basically what you see here, so what is the difference between this diagram and this? One more line. And here we may say that by order of magnitude, here we are. And point B, corrugated regime flame starts and it's changing. So at point where you may see here that here, below this solid, very solid dark line, instability develops. Above it, instability would not develop because turbulence will not allow instability to develop. Definitely there will be no instability here because there is no flame here. Here it might be, but it could not because of turbulence. Turbulence killed it. And here we introduce so-called number beta. We call it beta, we call it Bychkov number because of belated Bychkov, who really, he calculated this, and basically what is it? Number beta shows relation between turbulent and laminar flow. If beta is larger than 1, it means that turbulence killed the real and down instability. If beta is less than 1, it means that instability still develops. But it develops, but it is modified by turbulence, and here's how it goes. Do you understand this? Does it make sense for you? So please remember this diagram, how it looks like. And also, this diagram shows numerical calculation. So basically, this diagram here axes are different, but it shows numerical simulations. Because you may know that when you simulate turbulence, there are different ways how you approach it. There is direct numerical simulations when you resolve all scales. And there is larger simulations when you actually should model small, when you simulate large scales, but model small scales to because of some kind of filter. So to do it, what you should do? You should know how to select this filtering size. And definitely, when you talk about combustion, in addition to turbulent scale, like Kolmogorov and integral, you should deal with combustion scale. So basically, this diagram, what is here, it's a really counterpart of this diagram. What we plot here? So this axis show delta, which is a filter size. This is a size at which is your grid size, for instance. And LF is a flame thickness. And what you put here, it's your Karlovitz number, which is a measure of turbulence, how it develops. So what happens, and let's look at it. What happens here? If you are here downstairs on the small regime, so what we say here? Here we say the delta is less than flame thickness by order of magnitude. So delta here is actually less than active reaction zone. What is it? It's DNS, direct numerical simulation. It means that now your grid size is so small that it will resolve Kolmogorov scale, and it will resolve active reaction zone. It will mean that you resolve everything. Here it is. Now, and here you see the L-axis shows delta is equal to delta, means that the size when grid size is equal to active reaction zone. And here delta equal to eta means that delta equals to Kolmogorov scale. So if now let me go clockwise. What I'm dealing here, this is resolved turbulence. Because what does it mean? It means that my grid size is less than Kolmogorov scale. It means that I do resolve all turbulence. So it's like DNS. But why it's not exactly DNS? Because my Kolmogorov scale here may be larger than flame. So it means that I don't resolve all the flame anymore. If I can continue going clockwise, what does it mean here with this filter size? Here, what we talk about corrugated flamelets, and here that what we talk about thin reaction zone. Remember these regimes? So here I am. So here it means that I don't need to resolve flame structure, and here I need to resolve flame structure. And actually what happens here? Here we have broken reaction zone, or what we call well-styled reactor. What does it mean? It happens that Kolmogorov scale here is equal to active reaction zone, so the vortices penetrate the flame. And what you have here? Here Kolmogorov scale is equal to flame thickness. Here Kolmogorov scale is equal to active reaction zone. So you may see. So basically this is wrinkled flamelets. This is corrugated flamelets. This is in reaction zone, and this is broken reactor. And classical flame from experiments typically occur here. You may see it's corrugated flamelet and thin reaction zone. Okay, I think that, so please ask me questions. It's good. So that's how regime diagram look like. And what we will be doing next for these regimes? We will try to describe how flame propagates. We will try to find flame velocity as a function of different parameters. And you may realize that when I calculate flame velocity, so what we want? So in the standard idea, standard assumption here is the following, that we want to calculate turbulent flame velocity, what we call ST. And to find it, we will scale it by what? We will scale it by laminar flame velocity, correct? What is laminar flame velocity? You know it, it's echelon parameters, even planar flame doesn't exist in reality, it's our approximate values that we have. So do you agree that we better measure corrugated flame velocity by planar flame velocity? So we'll be looking for this ratio, provided that SL keeps your information about chemistry, about internal flame structure. And we'll be looking for this value like a function of what? Like a function of turbulence. What does it mean, function of turbulence? It should depend on turbulent intensity. And again, when I talk about interaction with turbulent intensity, turbulent intensity should be scaled by some value which is appropriate for me, true? And what value is appropriate for me? It's laminar flame velocity. So we will be trying to look for this function, and then we will realize, is it a good approach or not? Maybe not too good. And that's what we'll be starting considering. Okay, please ask questions. I do want you to remember this, and I will post this lecture. It's really some important lecture, and if you don't get it, please listen to it twice, thrice, or whatever you need, because that is something important. And so, like, I will start putting all these notes. So let me stop sharing the screen now, and please, there are some chat questions here. Just answer yes. Okay, so please, any question at this point? I know it's difficult, but please try to pick this up. It's an important topic. Please try at least. Any question? Everybody understood everything? I'm skeptic about it, but still, please try. That's what we have. We talk about fundamentals of combustion, fundamentals. I don't expect you to understand everything. I want you to have basic idea. But turbulent regime diagram is something that I really want you to know. Okay, so if this is the case, let me please write up now. I will finish it, and I will see you on Thursday. Please come. Please do your homework number 4. and please bring your questions. So let me try to finish Turbulence this week. I will try. If not, we continue on Tuesday, but we can finish it. And after this, it will be 3 weeks left, but we'll still have several lectures, but most of them will be more simpler. So we'll just talk about flame propagation in channels, in pipes, in conduits, and different ways how you promote and suppress flame acceleration. Let's do it. Okay, thank you for today, and let me stop.